This video is taken.
All right. So, recording has started. First, the calendar. The calendar is in 2 words. Maybe 3 words. A hot mess. So, and it's probably not going to get any better next week because we're on short periods. So, the most immediate and like insightful or impactful to you is the fact that this quiz that is scheduled for Friday is not going to be Friday. We're going to push it to Monday. So you will have to take it in class on Monday. It is an open no quiz. Right? We'll see how far we get. We may gather some data on Monday, but depending on the short periods and how long the quiz takes, we may not be able to gather some data from the lab on Monday. So this is going to be a very fluid situation throughout the next week. I think that's going to change probably quite a bit. Right now, I have the test written down for Friday, but I would say at this point it's probably not looking good for that test on Friday. We'll just have to wait and see what happens.
Okay.
So I'll keep you. I won't I won't come in and say, hey, the test is today. All right, I'll give you a little warning. So.
Is it the end of the quarter?
The end of the quarter is 2 weeks from today. Yes, March 23rd. So this test, when it happens, whether it's on Friday or whether it's the following Monday or Tuesday, whenever it may happen, that's probably going to be your last grade for the grading period. So you have this lab that you turned in that I haven't graded yet, the Lab Plus lab. Then the quiz, the Intro to Mechanics quiz, the one I just gave back to you, so that's in the grade book.
You haven't graded the back and forth?
No, I haven't graded it yet. You just turned it in.
Oh, okay. I'm thinking of the first.
So I graded it, Christian, I put them on this morning. So that quiz is on there. So I have to grade this lab. You're going to take this quiz on Monday. The lab, the time position graphs, we'll finish that up next week sometime. So that'll be due sometime next week. And then this test. So you've still got 2 labs that have to go up, another quiz, and a test before the end of the grading period. Yeah.
So wait, the grading period ends on the 16th?
No, it ends on the 23rd.
So we're just taking it.
Yeah, I don't know. Like I said, we may end up taking the test on Monday or Tuesday of that week.
Oh.
And we'll start next week. So, good. Not yet. I'll work on it. Yes. All right. With that being said, let's go here. Over the past couple of days, sorry. It's all right, over the past couple of days, we have used these objects on the ramp and this example of something falling straight down in the air to establish a relationship between 3 things. Okay? Actually, 4 things if you want to count that way. But if you look at the front page of the problem set that we've been doing for the past couple of days, up at the top, it's labeled as relationship between velocity and acceleration. I should probably change that because we're really looking at the relationship between more than that, right? We're looking at the relationship between velocity and acceleration, but what else have we been discussing as well? Distance or displacement, depending on what situation we're talking about, right? And then there's really one other factor that we've been including in this as well. The speed and velocity are kind of the same thing. It's the time factor, okay? So really, we're looking at the relationships between velocity, acceleration, displacement, and time. And at the end of class on Tuesday, and then continuing in yesterday, we established that there is a couple of mathematical ways that we model the relationships between velocity, acceleration, and displacement, and time. So the first one we talked about was this equation, right? Df is equal to di plus a times t. And that's relating for us the velocity at 2 different times, the beginning and the end of whatever time frame we're talking about, and the acceleration at the time. Okay? Good there?
Yeah.
Then the second relationship that we've been talking about was this one. Delta x is equal to bit plus 1/2 a t squared. So now we start looking at relationships between velocity, acceleration, time, and then what that says then about the distance or the displacement that that object experiences over that time frame. Are we good on these relationships?
Yeah.
So the first one, Allison, allows us to figure out what the velocity is going to be at a certain moment in time. Yeah, the speed, if we want to call it speed, but sometimes we'll see today that it's a better description of it is velocity. We'll talk about why in just a second. We're going to use those today to help us explain some more concepts. Okay? Yeah. One of the things we talked about was in developing these relationships and looking at the relationships, all the time frames that we've dealt with have been like 1 second intervals, right? It's been 1 second, 2 seconds, 3 seconds, 4 seconds. And that's fine for developing the pattern. But what these equations allow us to do is to take that pattern that we see at regular 1 second intervals and then apply it to any time frame. So if I want to know how fast something is going at like 3.762 seconds after I've dropped it, I can figure that out. Because I've established the pattern, now I get a little more specific based on the time that I'm looking for exactly. Okay. Good there so far? All right. Let's check out the problem set that I gave you yesterday that we didn't get to. I refer to this as the Ant Mini edition because Ant Mini is there on the front. Okay. So first, I would just like to preface this with all of us should really have an Ant Mini because Ant Mini is handing out 10 spots every second, which $10 per second. It's a pretty good rate. So if Ant Mini gives you $10 per second for 4 seconds, how much money are you going to have after 4 seconds?
$40.
You're going to have $40. Right? We'll make that one green because money's green. Okay. So, the next question I hope that we can pick up or that we can get the answer to based on what we've done over the past couple of days. A ball is dropped to rest and picks up speed at 10 meters per second. After it falls for 4 seconds, how fast is it going? It's going what?
40 meters.
40 meters per second, right? So it's going 40 meters per second. And remember, now, not square, because it's velocity, right? How fast is velocity? Okay? Now remember, yesterday, we talked about the idea that gravity causes this acceleration, right? That when gravity is acting on an object, it causes there to be an acceleration of 10 meters per second squared. Or we also talked about that we could write it like this, right? 10 meters per second for every 1 second. That's the acceleration caused by gravity. Good there? Okay. We got to remember that going forward. This number right here, this acceleration value, this is the acceleration of gravity. This is how much gravity causes the velocity of an object to change for every second that goes by. Right? Then you know that if we just drop an object, what's going to start happening to it? It falls. And as it falls, what happens to its speed? Faster, 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 faster. So gravity causes an acceleration. It causes this acceleration specifically. That's the number for gravity. 10. It's actually a little bit less than 10, right? We talked yesterday, but it's actually this number right here. Okay? But 10's a lot easier to deal with. So that's its acceleration value. Okay? Chris, go ahead. So, Chris, in another class we went through this, but that's the acceleration caused by gravity. So if gravity is the only thing affecting an object, they will all experience the same acceleration. When you're dropping something light, like a feather or a paper, now it's gravity plus the air resistance that it runs into, so it doesn't experience that acceleration. However, so here, we'll go to different books. So, with the two different books, right? Heavier book, lighter book, right? But the effect of air resistance on these books is pretty minimal because they're pretty heavy and stuff like that, right? So if we drop them at the same time, okay, they cause that same acceleration. Now, like you said, okay, if we drop something that appears to be heavy and appears to be light at the same time, they don't experience the same acceleration. Okay? But that's not gravity's fault. Okay? That's air resistance's fault, because gravity isn't the only thing affecting the motion of that object. But we can take it and use the same objects, right? We haven't changed how heavy this object is, right? What? I just changed the shape of it, so now it's not as affected by air resistance anymore, right? So gravity causes the same acceleration. When other things enter into it, then we have to sort of account for those. But for all of our stuff today, let's just assume gravity is the only thing acting. So we can assume that acceleration. So, for two reasons. One,
Terminal velocities are not increase.
one, so we have two reasons. One, when that object falls, it starts going faster and faster and faster. Gravity is causing it to accelerate. But one of the problems that it encounters is, as it's going faster, it starts running into air more often. Does that make sense? So it gets slower down because of that. It's like when you run in the rain, sometimes you may get wetter because you're running into a bunch of raindrops that you never would have hit if you weren't going that fast, you know? So that's sort of what happens when the penny goes. It like runs into air, and that air slows it down, and we actually get to a point where we refer to it as the terminal velocity, which is a concept that we'll deal with way in the future. Okay.
I know.
And for the other reason why is because they tried it on MythBusters. They said so. If MythBusters said it.
Can we watch that video?
They probably didn't drop it on anybody. They probably dropped it on that little like jelly thing that they make.
It's
you
called
know?
Buster.
Buster, you know.
Most,
Yes.
that's their dummy, not their ballistic
No, they don't. If you have a pound of bricks and a pound of feathers, they weigh the same. That. Because a pound. Now.
Oh, that makes sense. Sorry.
Kenny, that's exactly the same concept that we talked about with like a mole versus a gram.
Okay.
1 gram of carbon dioxide and 1 gram of oxygen, they weigh the same, but there's not the same number of molecules. All right. Now. All right. Here's where degree of difficulty starts increasing. Okay. For number 3. Actually, number 3 is really not that hard. Most of you can get number 3. Okay? If you have $20 and Uncle Harry gives you $10 each for 3 seconds, how much money do you have after 3 seconds?
40.
Oh, yeah, not at that rate. I feel like, like now that I'm an adult, like my aunt gives me $50 on my birthday. She's my godmother, so not all of my aunts give me $50. All right, hey, come on. Hey, time is wasting. We gotta get this done. Sure. All right, are we good at number 3? I hope.
Yeah.
All right, now let's talk about number 4. Okay. Very similar to the concept that we just discussed. Gravity is going to cause an acceleration on any object, heavy, light, whatever it is. Okay. But the one thing that we have to know is that gravity will also cause an acceleration on something that's already moving. Just like when we went here, right? When we dropped this ball off the cliff, just because after 1 second it was already moving at 10 meters per second, did gravity stop accelerating it? No, it keeps making it go faster and faster and faster. Okay? Even if it's already moving. So if we take back here to number 4, it says a ball is thrown straight down with an initial speed of 20 meters per second. So now instead of just dropping that object, we're actually throwing it downwards with a speed of 20 meters per second. But just because it's already moving, that doesn't mean that gravity doesn't affect it. Gravity still causes it to accelerate. gravity still causes it to accelerate at what rate? 10 meters per second per second. So if a ball is already moving at 20 meters per second, in 3 seconds, what's gravity going to do to it? Make it go faster, each second causing it to increase by how much? 10 meters per second. Because that's what gravity does. So at the end of 3 seconds, it will be going 50 meters per second.
I thought if you.
Nope. Because 3, what does gravity do each second? Increases it by what? 10. So at the beginning, it's going 20 meters per second.
30.
Then 30, then 40, then 50.
That's what gravity does all the time.
Gravity does that all the time, regardless of what it's actually doing currently. Okay? Anthony, go ahead.
How do you know it's increasing?
Because
That's-
it's 10 meters per second.
That's this. That's what the acceleration of gravity is. The acceleration is the change in the velocity. Okay? Megan, go ahead.
Is there a point where the acceleration exceeds gravity? Or is it-
Not if gravity is the only thing acting on it. Here on Earth, we have things where I think you meant the velocity, right? Did you mean that the velocity will stay the
I
same?
thought like when you say if you were really, really high.
Yep.
You don't.
You will not continue to keep going faster and faster and faster, but not because of gravity. That gets into the same thing we talked about with the penny, when Miriam was asked about the penny. That when you skydive, you won't just keep continuing to gain speed until you hit the ground. Okay, obviously the parachute and everything like that. But you run into the air that we have here on Earth, and that causes gravity's pulling you downward, but the air is pushing you upward. So eventually they'll balance each other out, and you won't gain any speed at all. You'll just keep falling at the same rate that you were before. That gets us, Megan, that gets us a little bit more next chapter. We're going to talk about forces. But if we could get rid of the air, then yeah, you just keep going faster and faster and faster and faster and faster. Okay. Chris, go ahead.
The wind going up at 60 per second, can you just stay still?
Kind of. Although the wind has to be going up fast. That's not quite, but yes. Have you ever seen pictures of like there's some kind of chambers, kind of looks like a big trampoline, and like there's a big fan on the floor, and you can kind of like float. You know, almost like you're skydiving.
I was about to do that, but it costs so much
Yeah.
money to do that.
Allison, go ahead.
So the reason why we use the gravity in number 4 and the number 2 is because before you like drop, like you throw it and then you just drop it.
Right.
Okay.
Yeah. So
you're
so-
you're doing it and the other one.
Allison, do you want to see it mathematically? Okay. So number 2, it says how fast is it going, right? So what are you looking for in number 2? If it says how fast, it's asking you to solve for a what? How fast is its velocity, okay? And more specifically, it's asking you to solve for the final velocity, okay? So here's that formula that we put up on the board before, right? So for question number 2 on that previous page, this is our unknown, right? EF is our unknown, okay? In number 2, what does it say about how the object starts? If it's at rest, or if we drop it from rest, that means the initial velocity is what? 0. What do we know the acceleration is? Because it's caused by gravity, right? And then how long does it fall under the influence of gravity? 4 seconds, right? So if you have 0 plus 10 times 4, that means that the final velocity is equal to what?
Oh, sorry.
40. Okay? Now, for number 4, right, it still wants to know how fast is it going, right? But now, so that means that df is still our unknown. But now, what does it tell you the initial velocity is? 20, right? Regardless of the fact that it's still moving, the acceleration is still what? No, what's the acceleration?
10.
The acceleration is still 10, it's still gravity, right? But then what's the time that it runs for? 3 seconds. So now you've got 20 plus 10 times 3, which is what? 30. So you got 20 plus 30. So the final velocity is going to be 50 meters per second.
Gravity and acceleration in this case are always equal.
Gravity is causing the acceleration. That's why it's always that 10 meters per second number, per second squared number.
Can it be like a negative 10 per second, like when you...
Hold on 1 second for that thought. Hold on 1 second for that thought. All right, are we good there? Okay. Accelerator. Hold on 1 second. That's like the next question. All right, good there in 3 and 4? Okay. I'm assuming most of you can probably do 5 by yourselves, right? You have $50 and you pay Aunt Minnie $10 a second. Aunt Minnie was so gracious handing out the 10 spots at the beginning of this speech. Now she wants you to give it back, right? And if I recall, she gave you $40, but now you have $50, and she wants you to pay all 50 of it back. Great. Okay.
No, she's making.
So,
Well, how many?
yeah, interest. Right? So, when's your money gonna run out?
Never, because don't give the money to everyone.
Never. So,
Just slap her and take the rest
Oh,
of
so
it.
one.
okay? So, if you have $50 and you have to pay Aunt Minnie $10 per second, how long is it gonna take before your money runs out? 5 seconds. All right. Now, here's when we start getting into numbers. Here's when we start getting into some signs, things like that. Okay. All right. You shoot an arrow straight up at 50 meters per second. When will it run out of speed? 5 seconds is the right answer, Sam. Do you understand how you got that?
Yeah, because
Sam, would you like to explain how you got it, or do you want me to do it?
I mean, I'll explain. I don't know fully that well.
Okay.
But
So, go ahead.
It starts at 50 meters per second.
Right.
And then, as you know, every time it's like decreasing, it's 10 meters per second. So after, like you have to subtract 10 from 50 each time. I don't know.
Yeah, that's right. In this case, which way does gravity, well, not just in this case, in any case, which way does gravity pull on things? Downward, right? In this case, which way is the arrow going? Upwards, right? So in this case, gravity causes a change of 10 meters per second for every second that goes by. What kind of a change is it going to cause in this case? It's going to cause the arrow to do what? Well, it can't go straight down to begin with, right? If it's going up and gravity's pulling down, what's going to happen to the arrow? It's going to slow down. How much is it going to slow down each second? 10 meters per second. Okay? So, let's go here. Let's do this. Okay? If we look at it mathematically again, right? Number 6, it's asking you for when will it run out of speed. So what are you trying to solve for in number 6? The time. If you run out of speed, what is the final velocity going to be? 0. What was your initial velocity? 50. But now we have to start taking into account 50 which way? Up, right? Because it said, no, it said in the problem that you shot an arrow straight up, right?
That's not.
Generally, yeah.
I did that once. And
Well,
it's
yeah,
so
you have 10
awful.
seconds to get out of the way.
It's so cool because you shoot it up and then for a second it stops and it comes down. It's like, oh, shit,
Actually, that's another thing too.
Yeah, they were playing chicken and one of them got it.
All right, so it says you shoot it straight upwards at 50 meters per second, so that's your initial velocity. But which way is it going? Up. So we're probably going to call that what? Which way is it going? Up. So we'll probably call that positive 50, right? But plus, what's the acceleration? It's 10, but which way is the gravity pulling on it? Negative, right? So negative 10 times t, right? 'Cause we're solving for t in this problem. If you solve this problem, what do you end up with for t? 5 seconds.
Wait, Mr. President, why
Yes.
is it
Because, Allison, when did we say something reaches its highest point? What do we know happens up at the top of its motion?
It stops.
It has to stop, right? That's how we know it gets to the top of its motion, because it stops, right? So that means that the arrow's speed after 5 seconds will be 0 meters per second. Now,
Because that's when it stops.
that's when it stops, right? Now, if it's up at the top of the motion, 5 seconds after you shot it, okay? We talked about the other day, when that object reaches the top of its motion, its velocity is 0. Is its acceleration 0?
9.
No, it's not. It stopped, but what did we say it was doing up the top of the motion? It's ready to go back down. It's changing directions, right? Is gravity still pulling on it up at the top of the motion? Yes. If gravity pulls on it on the top of the motion,
Is it just like the force of it going
it's making sense to the so.
He's watching over.
Yes. So, if an object is at rest up at the top of the motion, which is 5 seconds after we shot it, after 6 seconds, 1 second after it was up at the top, it's going down. How fast is it going down, Allison? 10 meters per second. And then after 7 seconds, it'll be 20 meters per second.
Yeah, I understand.
I'm good at throwing motorcycles.
Good.
No, it's not. I see.
Look at it.
All right, now, let's get into the harder part.
This is hard. Tomato.
All right, let's get into the harder part. Okay? Let me grab this guy here. This. And then grab these two. Sorry for the delay, everybody. Okay. The next part. It's down at the bottom, free fall distance. So it says, speed is one thing, distance is another. Where is the arrow you shot up at 50 meters per second when it runs out of speed?
Just do the distance formula.
Yep. So now let's do it conceptually first, okay? So we've established the fact that right when he shot it, how fast was it going? 50 meters per second. And then it goes up, 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 up. And then up at the top here, it's going how fast? 0 meters per second. Now, just like we did on the ramp, right? If we look at this section here, what is the average velocity during this time?
25.
The average velocity during that time is 25 meters per second. How long does it take? How long does this trip take? 5 seconds. So if we were going an average of 25 meters per second for 5 seconds, how high up in the air does this arrow go? 125 meters.
Wait, what? So you did it in 5
Wait, how do you know that this
That's 5 seconds.
Oh.
Kennedy, we already established that if it's going up 50, it's going to decrease by 10 meters per second for every second that goes by, right? So 40, 30, 20, 10, 0.
Would the total trip take 10 seconds then? Because you have to go up 5 and then down.
All right, Allison, go ahead.
So, to find like the, I guess the distance that you have to find like the average that's going up and then
That's one way to do it. Okay. The other way, Allison, that we could do it is we could use stop. We could use this formula, right? So here, okay, although this formula gets a little bit confusing for this problem, so I'm going to skip it right now, but we could use this formula as well. Okay. In this problem, VI would be what? Not just 50, positive 50. We've already established that the time would be what? 5. How am I supposed to break it down? So this is positive 50. This is 5, right? Plus 1/2 times A. What did we say A was? It's negative 10, because which way is gravity pulling? Gravity's pulling downwards, right? Times the same 5 seconds squared. When you figure that out, any guesses what you get? You get 120.
I don't get how you get that velocity.
Alex, if we go here, right? We know two velocities. We know it's going 50 down here at the bottom. We know it's going 0 up at the top, right? There's two velocities we know. All we do is we add those two numbers together and divide by 2 to get the average.
So we don't have to worry, like, when we're trying to, oh, that's for acceleration. That's how I get that.
All right, for number 2, how high will the arrow be 7 seconds after being shot? So we've already established that it's going to go up. It's going to take 5 seconds to go up, right? But then, as soon as it hits the top, what's going to start happening? It's going to start coming down, but it's only going to come down for 2 seconds, right? What was it doing up at the top here? Well, yes, but its velocity is 0, right? After 2 seconds,
No, because it.
because Sam, what does gravity do to the velocity? It changes it by how much?
Yeah, but when it says how high will.
Now, yeah, we're not there yet.
Oh,
Right.
sorry.
So this is what it's doing between 5 seconds and 7 seconds, right? Sam, what would be the average velocity during this portion of the trip? The average velocity is 10 meters per second. Sam, how long does this portion of the trip take? 2 seconds, right? So times 2 seconds, so how far does it go down? 20 meters. Now, the question says, though, how high will the arrow be, right? So the answer, Grace, is going to be what? 105 meters. Because it went up 125, but then it came down 20. Right? Is that good there? Okay. All right, let's see if we can do these last 2 questions real quick.
Why would he rush them?
That's why I'm saying, that's why we have to rush them.
Wait, you guys went through like a positive, right?
Now, Caroline, if we're using that, in that one, it's just asking how high. So if we talked about the displacement, if that question has to do with the displacement, then you would have to say positive 105. But for now, it's just asking you for basically how high above the strikes. Okay? All right. Actually, here, I'll do this. Okay? Instead of trying to squeeze these last 2 in, this weekend, I will post answers to this and the back side. Okay? I'll post answers to this side and the back side. That's your homework. That'll help you study for your quiz on Monday. Right?
Would you like to see the funny picture I drew?
10:45, yeah. It's not asking for a speed there. It's asking for how far.
I know, I'm 5.
Mr. Toys,
So, just so we got it clear, right? Over the weekend, I'll post answers to the remainder of that sheet plus the back side. Quiz on Monday.
would you like to see a funny picture I drew? I kind of disgraced Monty